Welcome, this is Basics Revisited, a carefully curated presentation. Our theme today is inequalities. We will travel through every type of inequality encountered in Class 11, Class 12, and competitive mathematics. An inequality compares two expressions using less than, greater than, or their equal counterparts instead of an equals sign. Unlike equations, inequalities yield a range of values, a set of numbers forming an interval on the number line. The most important rule: when you multiply or divide both sides by a negative number, the direction of the inequality sign reverses. Our journey covers 6 types: quadratic, rational, absolute value, higher degree, logarithmic, and exponential inequalities. Problem 1. We must solve x squared minus 5x plus 6, which must be greater than 0. We need all real values of x where this quadratic expression is positive. Our strategy: factorize the polynomial, find the critical points, draw number line, test signs, and write the solution. First, we factorize. We need two numbers whose product is positive 6 and whose sum is negative 5. Those are negative 2 and negative 3, so the polynomial factors as x minus 2 times x minus 3. Setting each factor to 0, x equals 2 and x equals 3. These are our critical points. Since there is no denominator, all real values of x are in the domain. Sign check: before 2 the expression is positive, between 2 and 3 it is negative, and beyond 3 it is positive again. We use open circles at the critical points because the inequality is strict greater than 0, not greater than or equal to. Here is the number line. The critical points 2 and 3 are marked with open circles. The expression is positive in the first region where x is less than 2, and in the third region where x is greater than 3. The middle region between 2 and 3 gives a negative value, so it is excluded. Our solution is x in the union of negative infinity to 2, and 3 to positive infinity. Problem 2. A rational inequality. Critical warning: never cross multiply without knowing the sign of the denominator. The numerator 0 is at x equals 1. The expression equals 0 there, so it is included since our inequality is greater than or equal to 0. The denominator 0 is at x equals negative 2. The expression is undefined there, always excluded. Testing signs confirms x less than negative 2 and x greater than or equal to 1 both satisfy the inequality. Problem 3. The absolute value inequality. When the absolute value of v is less than or equal to k, the golden rule gives us negative k is less than or equal to a, which is less than or equal to k. Adding 3 throughout both sides gives negative 2 less than or equal to 2x less than or equal to 8. Dividing by positive 2, the sign does not reverse, gives negative 1 less than or equal to x less than or equal to 4. The greater than type works differently. When the absolute value of is greater than k, we get two separate cases. Case 1, 3x plus 1 is less than -7, giving x less than -8/3. Case 2, 3x plus 1 is greater than 7, giving x greater than 2. The union of both cases gives the final answer, two separate intervals stretching outward. Problem 4 uses the wavy curve method. Critical points in order: -3, -1, 1, and 2. The denominator zeros, -1 and 2, are always excluded. Starting from the right with positive, the sign alternates at each critical point because all factors have power 1. Reading left to right, the signs are positive, negative, positive, negative, positive. We need negative regions, so we select -3 to -1 and 1 to 2, all endpoints excluded. Problem 5. Higher degree with an even power factor. Notice x minus 1 is squared. An even power factor never changes sign, so at x equals 1, the curve touches the axis but does not cross it. Signs right to left, positive beyond 3, negative after crossing 3, stays negative after crossing 1, positive after crossing -2. We want less than or equal to 0. The solution is the closed interval from -2 to 3. Problem 6. Logarithmic. First establish the domain. Both arguments must be strictly positive. Combined domain x greater than 3/2. Since the base is 2 greater than 1, the logarithm is increasing. Inequality direction is preserved when we remove the log. Comparing arguments directly gives x greater than 2. This lies within our domain, so the answer is x greater than 2. Important: if the base were between 0 and 1, the inequality sign would reverse. Problem 7. Exponential. Write 9 as 3 squared. Base 3 is greater than 1. Compare exponents directly. The exponent inequality becomes x squared minus 2x minus 2 less than 0. Roots at 1 minus root 3 and 1 plus root 3. Parabola opens upward. Expression is negative between the roots. The solution is approximately -0.73 to 2.73. Now the real learning begins through practice. Here are the first 6 questions. Questions 1 through 4 are foundational quadratic, absolute value, and rational inequalities. Questions 5 and 6 are of medium difficulty. Use the methods we have discussed: factorize, find critical points, draw the number line, test signs, write the interval. Questions 7 through 12 medium to competition level. Question 7 needs factorization by grouping. Question 8 is logarithmic. Question 9 has even and odd power factors. Apply the wavy curve carefully. Question 10 uses an exponential with a fraction base. Question 11 combines absolute value and quadratic. Question 12 is the most challenging logarithm with base less than 1, where the inequality reverses. And that brings us to the end of today's session on inequalities. We have covered quadratic, rational, absolute value, higher degree, logarithmic, and exponential inequalities. The method is always the same. Understand the structure, find the critical points, analyze signs, and express the answer as an interval.